Okay, here we are for our second lesson of chapter 2, and I think that you liked this lesson because it is less tedious than last time. So today we are going to continue talking about derivatives, but with a focus on some of the basic differentiation rules. So what you're gonna like is there are some mathematicians who have come before us who have figured out some more efficient ways of finding derivatives rather than using the limit definition of the derivative that we did last class. So first we need to talk about the notation a bit. So there are different notations for derivatives. We did go over this, so this is review, but it is really important to get this notation right. So we have this notation, which we read out loud as f prime. Sometimes you'll also see it as f prime of x, right? So these all mean the same thing. F prime of x is a little bit more specific because you can actually show what the input is. And then if we have a y, we might use y prime instead. But you could use it with any letter that you're given. So today we're going to be dealing with position and velocity a little bit. So for velocity, right, you could say v prime and so on. The other notation, the Leibniz notation, is the one that looks like a fraction. So if we were finding the derivative of y, we could write it like this, d dx of y, or that's equivalent, it's the same thing as writing dy dx, right? So these mean the same thing. It means the derivative of y with respect to x. Okay, you could also do the derivative of f of x with respect to x. So all of these are just notations that mean the derivative. Okay, first one, I'm just gonna tell you what these derivatives are. This is kind of cool if you think about the graphs of them and the slopes. Maybe you can pause it and try to envision why this is true. If you don't feel like doing that, then you can just believe me. The derivative of sine is cosine, and the derivative of cosine is actually negative sine. We are gonna end up using this so much this year that you will memorize them. So a lot of chapter 2, we are dealing with rules that at first you might be like, oh man, this is a lot to memorize, but you're gonna use them so often that they will become second nature. Okay, so last class we used the limit definitions of the derivative to find the derivative of a function. It was quite a tedious process. Fortunately, we have lots of rules that allow us to find derivatives without direct use of that limit definition. You are still expected to know the limit definition, but you are not typically going to use that limit definition to find your derivatives. Okay, so starting off with the constant rule, anytime you take the derivative of a constant, you get 0. So if your function here, the function s of t is 0, then s prime of t, right, so that means the derivative of the function s will also be 0. F of x equals negative 2/3, that's just a constant, therefore f prime of x, the derivative of f, will be 0. And for c, we have y equals 10 pi. Remember, pi is not a variable, it's a constant, so 10 pi is just a number, therefore y prime, derivative of y, will just be 0. Okay, and if you recall what a derivative is on the graph, it's the slope of the tangent line at a point. So if you have a constant, right, the graph of a constant will always be a horizontal line, and the slope of that line, no matter what point you're dealing with, right, the slope of that line is always 0, and that's why the derivative of a constant is 0. So the more you can make the connection between what is going on with a function and its graph and its derivative, the better off you're going to be. Okay, now the power rule. This is one of our most frequently used rules. If you have the derivative of some polynomial, so some variable x to a power, what you do is you bring that power in front, right? So that's where that n comes from, and then you decrease the power by 1. Let's practice. So to find the derivative of y equals x to the 7th power, my y prime, my derivative of y, is going to be, I'm going to bring that 7 in front. It becomes a coefficient. And then I decrease the exponent by 1. So instead of 7, it'll become a 6. And that's the derivative. If you wanted to, you could go ahead and do one of these using the limit definition and see that it works. But you don't have to do that. Okay, let's try this one. F prime of x equals, so I'm going to bring that exponent out front as a coefficient. I keep my x there, and then I have to decrease my exponent by 1. So negative 3 over 2 minus 1 is negative 5 over 2. Now, it is fine to leave your answer like that, but sometimes you're going to see it written in a different way. So there's lots of equivalent ways that you can write this, right? But in a free response, you can write it in whichever way. But in a multiple choice, you might see it written in a more simplified way, so you need to be able to identify if it's equivalent. So here, I'm going to, let me show this even more step by step, because I think some of us are struggling a little bit with some of our algebra skills. So when you have x to a negative exponent, that can become 1 over x to the positive exponent, and then you can squish these together into one fraction. Okay, you don't need to show that intermediate step. You can go straight from step 1 to step 3. Okay, now what about something like this? So for c, I would first rewrite my cubed root as an exponent. So that's the same thing as t to the 1/3. And then you apply your power rule. So I have g prime of t. I'm going to bring that 1/3 out front, and then I'm going to decrease my exponent by 1. So 1/3 minus 1 is negative 2/3. And again, I have that negative exponent, so I'm going to move that t to the 2/3 into the denominator. Okay, last one, and this is where I see probably the most mistakes when we're first learning derivatives, so maybe star this one. The power rule applies when that power is not in a denominator, okay? So 1 over x to the 5th, you can't just bring the 5 out front and decrease the exponent to a 4. Instead, you need to rewrite this as x to the negative 5 power. 1 over x to the 5th is x to the negative 5 power, and now you apply your power rule. So this will become negative 5, x to the negative, sorry, there was an ant on me. Oh my god, probably still is. Okay, sorry, crisis. So this is going to become negative 5 over x to the 6th power. And that's the final answer. So there you have the power rule. Now, what else? Now we're going to kind of like put this together. So if you have a constant in front of your whatever you're working with, okay, this is going to apply beyond what we're doing. For now, we're still going to just use it with the power rule. But if you have a constant multiplier in front, you can just move that guy out in front of your derivative. Okay, that only works with multiplication. So if you have u is a function, and c is a constant, then you can move that c out front, and then you can just take the derivative of whatever function is left. Okay, so here, what I mean by that is I'm going to just show this to you in maybe a way that makes sense, because you really, hopefully this becomes like, I don't know, logical to you. But for now, we're going to think about that 1/3, leaving it there, and then we're going to just take the derivative of the t to the 4th power. Okay, so the constant is unchanged. Now we're doing the derivative of t to the 4th power. That will be 4t cubed, and then squish it together. 4/3 t cubed. So typically, we're going to get comfortable going straight to this step if there is a constant multiplier in front, you don't need to show that first step that I wrote. So let's do one more. So let's say we had x of t equals, let's say 2x to the 8th power. I would here typically just go straight to doing it. So I'm going to bring the 8 out front. I know that the 2 is staying there and it's getting multiplied. So I just know that that's going to become a 16x to the 7th power. Right, and really what we did is we left the 2 there and we did the derivative. Oh God, that shouldn't be an x, that should be a t. T. And then I did my 8t to the 7th, and then I multiplied these. But usually we don't show that step. You certainly can if it helps you. Okay, and now putting it together even more, if you have the derivative of, and then you have all these different functions being added and subtracted, you can just take the derivative of each one. So when we're taking the derivative of this guy here, I'm just going to take the derivative of each piece. So 6x to the 4th power. For now, I'll write it out the longer way, just because we're still learning. So I have my 6 stays out there. X to the 4th, derivative of that is 4x cubed. Okay, minus, now we need to deal with this. This is just the same thing as 1/4 x squared, right? So that divided by 4 is also just a constant multiplier of 1/4. So I'm going to have my 1/4 out front, and I'm going to do the derivative of x squared, which is going to be 2x to the 1st power. You don't have to write to the 1st power. And then the derivative of 5, normally you wouldn't write this. The derivative of a constant is 0. Okay. Normally you wouldn't write plus 0. I'm just doing it because we're still learning. And now we can simplify this a little bit. We have 24x cubed minus that we have 1/4 of 2, which is 1/2 x. Okay, so y prime equals that. Okay. Believe it or not, we're almost done. So that is like the main goal of today, is just to be able to find some pretty simple derivatives of polynomial functions, also derivative of sine and cosine. Okay, so we will often use derivatives to find rates of change in word problems. And so you want to, again, I'm going to keep repeating this throughout the year, the more that you can make connections between what is going on with a graph, with your equation, and now also with a real world context, the better off you're going to be. So let's take some time reading through this together. Rates of change. A derivative is the slope of the tangent line. We've already learned that. However, it also represents the rate at which f of x changes per unit change in x, okay? So that derivative is the slope, which is also the rate of change. Last class, I think we talked about it as the instantaneous rate of change. We talked about average rate of change versus instantaneous rate of change. So derivative is the slope of the tangent line, and it's also the rate of change. Many applications of calculus involve rates of change, and one example is the rate of change of the position of an object moving in a straight vertical line under the influence of gravity. Okay, so the position of a free-falling object, we're going to ignore air resistance, under the influence of gravity can be represented by this equation here, where that little zero, the subscript 0, we call it v naught. Okay, v naught. So the initial velocity is v naught, and then s sub 0 or s naught is the initial height. Okay, so initial velocity, initial height. And then g is the acceleration due to gravity. So that's what that g is up in the first term. On Earth, the value of g is approximately negative 32 feet per second squared or negative 9.8 meters per second squared. In calculus, don't ask me why we use feet versus meters. I know in physics you use meters, so that can get a little confusing. But in the calculus world, we're still in feet. I should specify in the AP calculus world, College Board style, we're using feet. Okay, so S of t equals, let's write it. We have this negative 32 feet per second, so we're going to just substitute that in for g. Okay, so we're going to have 1/2 of that, which is going to become negative 16 t squared plus v naught t plus s naught. Okay, so this is the equation we're going to be working with. And again, this is representing the position. This is the position function. Position of an object, of a free-falling object. Okay, so I know I'm giving you a lot of information right now. Feel free to pause to digest if needed. Again, if you're into physics, you're probably like, okay, I already know some of this. So thank you for being patient. Now, another thing that's going to be important this year is velocity versus speed. Velocity is a vector. What that means is that it includes a direction. So you can have a negative velocity. Negative velocity would mean motion backwards or downwards, depending on what's going on. For example, let's say I am walking at a speed of negative 3 miles per hour. That just means velocity. That would mean that my motion is backwards. So maybe I'm walking backwards. Okay? So with a falling object, the velocity as it's falling is negative because it's falling downwards. Speed, however, will always be positive. So you don't usually say that your speed is negative. You just say that this is the speed that I'm going 3 miles per hour. Velocity is just indicating the direction forward or backwards. Okay, now you have some formulas. Up top, you've got average velocity. Average velocity is found by taking the change in the position divided by the change in time. Okay, so it is the average rate of change of position. Average velocity is the average rate of change that we learned last time of the position function. Okay, versus instantaneous velocity. Instead of figuring this out over a time interval, we want to know, like, at this instant, how fast am I going? Then we use derivatives for that. So you would be taking, right, this is that limit definition of the derivative. All this is the average rate of change. That is the average rate of change of position. And if you take the limit as the change in time is approaching 0, then that gives you the derivative. So for instantaneous velocity, we are taking the derivative of position function. Okay, so we're going to do a side-by-side comparison here. So we're going to find the average velocity and then the instantaneous velocity so you can kind of see the difference. A basketball is dropped. Well, hopefully nobody's doing this for funsies, but a basketball was dropped from the top of a 150-foot tall building. Find the average velocity over the time interval 1 to 2. When you're finding the average velocity, you have to be given a time interval. Step 1, before we can even find the average velocity, we need to know the position function. And sometimes that will be provided. Sometimes it might not be, so you should know how to write it. Okay, we just went over that in that box up above. So the position function is negative 16 t squared plus blank times t plus blank. Okay, remember this thing that goes here is initial velocity. If you are dropping an object, okay, the initial velocity is 0 because you are not throwing it. It's starting at a velocity of 0 because it's not moving. The initial position is what goes in this last spot. And in this case, that is 150 feet. So that's our function. You don't have to write the plus 0t. We're just putting that in our notes so we remember how we got this function. So I'm going to rewrite the function right here, simplified. And now we're going to find the average velocity by finding the average rate of change of the position function over the given interval. So all we're doing is, so average velocity will be s of 2 minus s of 1 over 2 minus 1. Change in position divided by change in time. Okay, you guys can take a minute to do that, or I'll just give you the answer, hopefully, that's right, negative 48 feet per second. All right, so you have to find s of 2 and s of 1 and then see what you get. Okay, that is average velocity. Now, instantaneous velocity. The instantaneous velocity, again, is the derivative of the position function. So a basketball is dropped from the top of a 150-foot tall building. We still have the same situation. Find the instantaneous velocities when t is 1 and t is 2. So notice when you're finding instantaneous velocity, you're finding it at a specific time rather than over a time interval. So write the position function if it's not provided. We already did that on the other side. So let's just write it again. Find the velocity function by differentiating the position. So before you go to plug in your times, now we want to actually find our velocity function. The velocity function will always be the derivative of the position function. So we're taking that function that we wrote up there, and we are finding the derivative. So you'd have to bring the 2 in front. So you'd have negative 16 times 2, which is negative 32, t to the first power plus 0, because the derivative of 150 is 0. So our velocity is just negative 32t. Find the instantaneous velocity at the given times. So we wanted to find it at time 1 and at time 2. So we have v of 1 that we're finding, v of 2. I'm going to show my work, even though maybe it feels silly. This is negative 32 times 1, which is just negative 32. Let's add on our units here, feet per second. And velocity at time 2 is going to be negative 32 times 2, or negative 64 feet per second. Okay. So at 2 seconds, the ball's moving faster, right, because it's been falling for longer. And remember, the negative just indicates that the ball is moving in a downward direction. Okay, now I have another question. Find the time required for the basketball to reach the ground. Okay, this one, I don't know. I think just sometimes it's hard for students to interpret what a question's asking. Like, what do I do? How do I find that? Find the time required. So you're solving for t. For the basketball to reach the ground. Okay, reach the ground means that the position is 0, because the position is representing the height off the ground. So if it's on the ground, the position is 0. So we need to solve for t when the position is 0. In other words, take your position function and set it equal to 0. So I'm taking my position function and I'm setting it equal to 0, and I'm solving. So I'm going to add the 16t squared. I'm going to divide both sides by 16. And then I'm going to take the square root, and because I'm taking the square root, I will get plus or minus the square root of 150 over 16. Okay, we now are going to ignore this negative because the time won't be negative, right? Can't be negative. We're not going to have a negative time. So we're only going to have our positive answer. And then you can certainly simplify that radical, really that's not an emphasis in this class. If it was multiple choice, would it be simplified? Sure. On a free response, you can leave it like that. Depending on if it's, calculator or no calculator, you would know if you should turn that into a decimal or not. So this is the exact answer, which feel free to simplify it. I'm not going to for sake of time. But I could also convert that to a decimal, which I just have my notes up from last year, so hopefully those are right, is 3.062 seconds. In our class, AP Calculus, the standard is to round 3 decimal places. Okay, now you can get a little calculator practice. This part is going to be really important. Find the velocity of the ball at impact. Okay, so we're finding a velocity, and we just found the time when the ball hits the ground. Right? The time when the ball hits the ground is this time that we just found. So we're going to plug that time in here. This is what's important. Anytime you are using a previous answer to find another answer, you cannot use a rounded answer. You have to use the exact answer. Okay, so here I am using a time I found in part B to figure out part C. I'm not going to use my rounded one, I'm going to use my exact one. So don't type in velocity of 3.062. I need you to use the exact answer, and your calculator is going to do it for you anyway, so it shouldn't be much harder. So I have negative 32 times t, remember that's our velocity function. So now we're just plugging that in. Now and I'm going to make a note here, substitute in the exact time, not the approximation. Okay. Then you punch that in your calculator and you see what you get. And I think you're going to get negative 97.979 with units. Here we're finding velocity, so my units are feet per second. So that's the velocity of the basketball when it hit the ground. Okay, so these are going to continue coming up throughout the year, this connection between average velocity, instantaneous velocity, and position. So make sure you kind of study this example to feel good about it. Hopefully the derivative rules were fairly straightforward today. And in the rest of the chapter, we're going to continue learning more rules so that we can differentiate more types of function, because right now we're very limited in the types of functions that we can find derivatives of. Okay, let me know if you have any questions. See you soon.